the deep silence of interstellar space, where starlight travels for millions of years before touching any surface, something breaks the cosmic monotony. A pale, faint, almost imperceptible shape crosses the void like a solitary traveler between galaxies. Automated telescope sensors detect a weak yet peculiar glow, different from what one would expect from an ordinary comet. It is the first signature of the interstellar object we will call 3I Atlas, the third recorded visitor coming from beyond our solar system. Thus begins a journey that blends fascination, uncertainty, and the promise of new knowledge. As the imaginary camera approaches this celestial intruder, the vastness of space unfolds in contrast. Colorful nebulae in the distance, dust filaments, young stars pulsing as they form. Against this almost mythological backdrop, 3I Atlas seems small, yet its quiet presence carries the weight of something rare. Interstellar objects do not orbit the sun like the bodies we know. They pass through, entering and leaving on hyperbolic trajectories, like forgotten messages launched from other planetary systems. It is this path, impossible to reproduce, that makes it so intriguing. Yet there is something more here. Scientists would quickly notice that this object is not just another point of light crossing the detectors. Its glow seemed to vary subtly, and its initial light curve, the record of its brightness changes, raised suspicions. It wasn't the moment to call it an anomaly yet, but there was already a scientific unease in the air, as if this newcomer carried an unwritten chapter of astrophysics. Questions begin to echo even before answers appear. At this moment, the documentary gains tension. The narrator observes that we are witnessing something that happens perhaps once in a generation. Just like Oumuamua in 2017 and Comet Borisov in 2019, 3I Atlas is a living reminder that our solar system is far from isolated. Crossing the cosmos is no trivial act. It involves gravitational forces, interactions with particles and starlight, and a past full of chaotic events. Each interstellar visitor is in itself a fragment of cosmic history waiting to be deciphered. As the object approaches the region explored by human science, telescopes such as Pan-STARRS, Atlas, and other professional observatories begin tracking it with increasing precision. The tension comes not from danger, but from the unknown. What will we see once we have enough data? Can its trajectory reveal its origin? Can its composition show how other planetary systems are formed? These questions drive the narrative, keeping curiosity alive as science prepares to confront the enigma. Space, however, does not hurry for us. 3I Atlas continues its silent motion, unaware of the interest it stirs. The light it reflects arrives distorted, scattered by dust and ice, carrying information that must be interpreted carefully. It is likely that this object traveled millions of years before encountering the sun, and every grain of material on its surface holds clues about environments so different we can barely imagine them. Physics, even with all its rigor, bends before the scale of cosmic time. And so, even before we know exactly what makes 3I Atlas so special, the mystery takes shape. There is a palpable sense that something recently observed doesn't fit perfectly into current models, not because it is impossible, but because it challenges the patterns we expected. Like the prologue to a great scientific riddle, this opening sets the stage for investigation. What do we really know about this visitor? What sets it apart from the others? And why is its passage through the solar system changing the way astronomers perceive the cosmos? When 3I Atlas was detected by the Atlas system in Chile in 2025, astronomers quickly realized it was not a common visitor to the solar system. Its movement across the sky indicated a hyperbolic orbit, a type of trajectory that does not close a cycle around the sun. This means the object was not born here. It came from somewhere beyond the heliosphere and will continue its journey once its passage is complete. This fact alone already establishes the interstellar nature of the phenomenon. To understand the importance of this discovery, it is useful to remember that only two interstellar objects had been recorded before, Oumuamua and Comet Borisov. 3I Atlas therefore becomes the third confirmed object coming from outside the solar system, an extremely rare event on human timescales. These bodies are fragments ejected from other stellar systems, possibly during planet formation. Thus, each of them carries chemical and physical signatures that can be completely different from what we know in local comets. The first analyses showed that 3I Atlas displayed clear signs of cometary activity. Instead of being an inert, rocky object, as some initially suspected, there was a coma around it, a cloud of gas and dust released by the action of sunlight on its icy nucleus. The presence of this activity made the study even more interesting, since active comets allow more direct investigation of composition, temperature, and dynamics through spectra and variations in brightness. Preliminary data from space telescopes indicated a composition particularly rich in carbon dioxide. Scientists observed that CO2 seemed to dominate the comet's activity, even surpassing water as the main volatile being released. This characteristic is considered quite unusual compared to traditional solar system comets, in which water generally plays the leading role as the nucleus warms. This abundance of CO2 suggests unique internal conditions, likely related to the distant cold environment where the object was formed. In addition to carbon dioxide, traces of water, carbon monoxide, fine dust, and sulfur compounds were identified. The detection of OH radicals, derived from the photodissociation of water, confirmed that the comet releases water vapor even at great distances from the Sun. This sensitivity to radiation in cold regions raises the hypothesis that some of these materials were trapped in more fragile surface layers, ready to sublimate with minimal energy. This behavior helps researchers reconstruct the thermal and mineralogical structure of the nucleus. Another relevant detail is its speed. 3I Atlas approaches the solar system with a hyperbolic excess velocity of approximately 60 kilometers per second, a typical speed for interstellar objects that have wandered for millions of years through deep space. During its passage at perihelion, it will come a little more than 1.5 astronomical units from the Sun, a position that will allow better observations but poses no risk to Earth. This safe trajectory has already been widely confirmed by independent orbital calculations. Finally, estimating the object's true nucleus size remains a challenge. The presence of the coma interferes with direct measurement, and values range from a few hundred meters to several kilometers in diameter, depending on the reflectivity assumed in the models. It is likely that the nucleus is small, similar in scale to the smaller comets that periodically visit the solar system. Even so, its composition and interstellar origin make it a unique research object, whose brief passage offers astronomers a rare opportunity to uncover materials formed in other corners of the galaxy. When astronomers began analyzing 3I Atlas's light curve more closely, something unexpected drew their attention. The object's brightness did not vary in a stable pattern, as would be expected from a conventional active comet. Instead, small irregular oscillations appeared at unpredictable intervals, suggesting sudden changes in the amount of gas being released. This kind of behavior is not impossible, but it is often associated with partial fragmentation events or with regions of the nucleus that activate and deactivate sublimation abruptly. The irregularity sparked early discussions about what might be happening. A second intriguing detail emerged from spectroscopic observations. The ratio between carbon dioxide and water was much higher than usual, and although this characteristic had been seen before, the rate at which this CO2 increased appeared to be rising non-linearly as the comet approached the Sun. This could indicate that different layers of the nucleus were being exposed, or that 3I Atlas contained internal pockets of volatile gases trapped beneath rigid crusts. Scientists avoided jumping to conclusions, but acknowledged that the exotic composition might point to formation processes very different from those of local comets. Another element that raised debate was a slight non-gravitational deviation detected in its trajectory. Active comets typically experience small accelerations due to jets of expelled gas, but the direction and intensity of this deviation did not seem to align perfectly with the visible activity. In simple terms, part of the observed acceleration did not directly correspond to the regions in the coma, where sublimation was most intense. This doesn't imply anything extraordinary. However, it forces researchers to consider irregular internal structures or jets channeled through deep fissures in the nucleus. As more sensitive instruments began collecting additional data, an even greater curiosity arose. 3. Atlas's activity appeared to begin much earlier than expected. At about 4 astronomical units from the Sun, a region where many comets remain mostly inactive, the object was already emitting significant amounts of volatiles. This early activation could indicate an abundance of CO2, which sublimates at lower temperatures than water, but the release rate suggested something more complex, possibly a combination of deep fissures, porous layers, and ultra-fragmented materials. Additionally, some observatories recorded a rapid increase in brightness over a short period of time, something astronomers call an outburst. These surges can occur when sunlight reaches an internal cavity, causing the abrupt release of trapped gases. In the case of 3I Atlas, the outburst was not enormous, but it was sudden and stronger than expected for a newly detected comet still in the early stages of approach. This phenomenon fueled the hypothesis that the nucleus was experiencing structural stress after an extremely long interstellar journey. Researchers also noticed small indications of coarser dust mixed into the coma, which often suggests that pieces of the nucleus may be breaking off. This possibility is not unusual in comets, but in the case of 3I Atlas, it could help explain the irregular brightness variations. Even so, nothing indicates a catastrophic fragmentation, only unstable behavior, consistent with the idea of an ancient body weakened by exposure to extreme environments throughout its travel between the stars. Finally, perhaps the most intriguing aspect is that no single model explains all observations simultaneously. The early activity, the unusual abundance of CO2, the non-gravitational deviation, and the sudden outburst form a set of characteristics that, although entirely plausible, require multiple hypotheses working together. Scientists acknowledge that 3I Atlas is not inexplicable, but it is different enough to challenge some expectations and demand more refined analyses. It is precisely this combination of real phenomena, still without a definitive explanation, that keeps the scientific mystery surrounding this interstellar visitor alive. One of the first hypotheses considered to explain the behavior of 3I Atlas involves the differentiated sublimation of volatiles, especially carbon dioxide. Since CO2 evaporates at lower temperatures than water, scientists believe the object may be releasing large amounts of this gas at distances where traditional comets remain almost inactive. This early release would create asymmetric jets capable of slightly altering the object's trajectory and causing irregular variations in its brightness. It is an explanation consistent with what is known about comets rich in light volatiles. Another plausible theory suggests that the nucleus of 3I Atlas may be highly porous, formed by layers of dust and ice that expand and contract as they absorb heat from the sun. This irregular internal structure would allow deep cavities to store pressurized gases, releasing them in bursts when specific regions warm up. This type of architecture is common in solar system comets, but the interstellar environment may have intensified the erosion, leaving the nucleus even more unstable and favoring the emergence of sudden outbursts. Some astronomers consider the possibility that the object is undergoing structural fractures as it approaches the Sun. After millions or even billions of years wandering through interstellar space, exposed to micro-collisions and cosmic radiation, the nucleus may have developed internal cracks that are now reacting to heating. As these fissures expand, pockets of gas and dust escape, creating surges of activity that could explain the sudden brightness increase observed. There is no evidence of total fragmentation, but the presence of small surface cracks is considered likely. Another physical explanation involves the Yarkovsky effect and non-gravitational forces generated by the comet's own jets. When a comet releases material asymmetrically, it receives small kicks that alter its path. Although this is expected, the unusual direction of these deviations suggests that the jets may be emerging from unexpected regions of the nucleus, possibly guided by craters or deep fissures formed even before its arrival in the solar system. This hypothesis aligns with models that describe interstellar comets as highly heterogeneous bodies. There is also a line of research exploring the idea that 3I Atlas may contain unusual chemical mixtures formed in stellar environments different from our own. Each planetary system has its own chemical fingerprint, and this influences the composition of the smaller bodies that form within it. If 3I Atlas originated in a particularly cold region, or one rich in CO2, its unusual activity might simply reflect a composition not commonly seen in solar system comets. This hypothesis does not require extreme phenomena, only the natural chemical diversity of the galaxy. A more dynamic hypothesis considers that the object may have undergone uneven erosion during its long interstellar journey. High-energy particles, impacts with microscopic dust and extreme temperature variations could have worn down certain regions of the nucleus more than others. This erosion would produce an irregular surface with weaker or exposed areas, allowing sublimation cycles that do not follow predictable patterns. Surface heterogeneity is a simple yet powerful explanation for the variability in its light curve. Finally, some theoretical models explore the possibility that 3I Atlas is going through a natural phase of gradual reactivation, typical of comets that spend long periods inactive. As it enters the sun's thermal influence, layers of accumulated dust begin to shift, exposing fresh ice that reacts more rapidly to solar radiation. This surface cleaning process can generate temporary erratic behavior, especially during the first weeks of observation. It is a hypothesis consistent with well-known phenomena, requiring no extraordinary assumptions, only the standard thermal physics of comets. 3I Atlas is not just another active comet. It is an extraordinary opportunity to study material formed outside the solar system. Since scientists believe that interstellar objects are fragments expelled during the formation of other planetary systems, each one carries information about processes that took place in environments very different from our own. Thus, investigating its composition and behavior allows a direct comparison of the physical and chemical conditions present around other stars, as if we were holding a fragment of a planet that never existed here. This comparison offers a unique window into the galaxy's diversity of worlds. The study of this object also helps refine models of comet formation and evolution. Solar system comets follow patterns that are relatively well understood, shaped by billions of years under the sun's gravitational influence. An interstellar body, on the other hand, travels almost entirely isolated for long periods, crossing cold regions, varying dust densities, and random magnetic fields. By observing how 3I Atlas behaves as it re-enters a bright, warm environment, astronomers can test theories about how radiation and stellar winds modify these bodies over the course of their history. Another important scientific implication arises from 3I Atlas's unusual composition, rich in carbon dioxide. This characteristic challenges traditional models that describe comets formed in the outer regions of planetary systems as being dominated by water ice. If CO2 is indeed such an abundant component, it could indicate that the stellar system of origin had conditions different from those we know, perhaps lower temperatures or molecular clouds with distinct chemistry. This type of information is valuable for astrophysicists studying how planets and comets form in different zones of a protoplanetary nebula. In addition, the irregular behavior of 3I Atlas helps put into perspective phenomena observed in other interstellar objects, such as Oumuamua and Borisov. Each interstellar visitor so far has shown peculiar characteristics. Oumuamua had a mysterious, non-gravitational acceleration, while Borisov resembled a more traditional comet, with a composition similar to those in our system. Now, 3I Atlas introduces a third pattern, richer in light volatiles and perhaps more unstable. These three cases show that there is no single model for interstellar objects, revealing a much greater diversity than previously imagined. The phenomenon is also relevant for astrobiology, although in a responsible way and without exaggerated speculation. Comets are important because they carry complex molecules such as organic compounds and amino acid precursors. By analyzing the chemistry of an object formed in another system, scientists can test whether certain compounds are common across the galaxy or whether they are local rarities. Although nothing indicates life or any biological component in 3I Atlas, the presence of simple organic materials could reinforce the idea that the basic building blocks of life's chemistry are widely distributed throughout the cosmos. there are also direct implications for future space missions. With the increasing detection of interstellar objects, the scientific community is discussing plans for interceptors capable of reaching and studying these visitors up close. Each new discovery helps improve our understanding of the speed, composition, and behavior of these bodies. Fundamental information for designing spacecraft that can maneuver and survive near them. 3I Atlas, with its rich and early activity, offers practical data on how such objects may react as they approach the Sun, something essential for planning fast, precise missions. Finally, the observation of 3I Atlas has historical importance. It enriches the scientific narrative about our relationship with the cosmos. Until a few years ago, interstellar objects were only hypotheses. Now we are already observing the third specimen, each with its own personality. The realization that fragments of distant worlds cross the solar system with relative frequency transforms our view of the galaxy. Instead of an isolated archipelago, we see an ocean in which material travels freely, connecting stellar and planetary histories we never imagined we shared. The story of 3I Atlas officially begins at the moment of its initial detection, when the automated system identified a point of light moving in a way incompatible with known solar system objects. In the first few days, astronomers focused simply on confirming the discovery, repeating observations and calculating a preliminary trajectory. As new measurements were obtained, specialists realized that the object was moving far too fast to be gravitationally bound to the Sun, immediately raising the possibility that it was an interstellar visitor. This early confirmation established the starting point of a true scientific race. In the weeks that followed, observatories around the world began recording the brightness of 3I Atlas continuously. Each new night of observation refined the orbit and increased confidence in the interstellar nature of the object. It was during this period as well that the first indirect signs of cometary activity emerged, suggesting the presence of a faint but growing coma. Astronomers then began prioritizing higher quality spectra in an effort to identify which molecules were being released by the nucleus. These early data fueled the first hypotheses about the object's composition. As measurements improved, the moment arrived for major space telescopes to take action. Infrared instruments detected clear signatures of carbon dioxide, revealing that the comet was dominated by this unusual volatile. From that point on, researchers began constructing specific sublimation models, comparing brightness variations with spectral emissions. At the same time, ground-based telescopes captured subtle changes in the coma, indicating that the object was becoming more active as it entered brighter regions of the solar system. This set of data consolidated a more detailed view of the physics involved. Sometime later, with more refined observations, astronomers identified a small non-gravitational deviation in 3I Atlas's trajectory. This moment marked a shift in the type of analysis being conducted. Attention moved from confirming the interstellar origin to investigating the causes of the observed anomalies. The scientific community began comparing the measurements with models of cometary jets, seeking to understand how gas release was influencing the object's path. It was also during this stage that small oscillations in the light curve gained prominence, reinforcing the idea that the nucleus was more dynamic than expected. As the approach to the Sun continued, new images revealed that the comet's activity was increasing more rapidly than traditional models predicted. This discrepancy led astronomers to organize international observation campaigns, synchronizing instruments across different hemispheres. High-resolution images obtained during this period allowed researchers to identify bursts of brightness, possibly associated with outburst events. These records became essential for the hypotheses that would emerge in the following months, helping explain the comet's seemingly unpredictable behavior. Over several months, additional spectra revealed the presence of water, coarser dust, and simple organic compounds, painting a more complete picture of the chemistry of 3I Atlas. With each new detection, the models were adjusted again, refining estimates of size, porosity, and the internal distribution of materials. It was at this stage that the idea became consolidated that the comet might possess complex internal layers composed of different types of ice that reacted to heat in distinct ways. The timeline of the investigation thus began to integrate chemistry, orbital dynamics, and thermal physics in a unified manner. Finally, with the trajectory well defined and the cometary activity being monitored with precision, scientists reached a moment of interpretive stabilization. The community began converging on a coherent set of hypotheses that explained most of the observed phenomena, while still leaving room for natural uncertainties. The timeline of 3I Atlas shows a clear progression, from the unexpected discovery through the interstellar confirmation to the recognition of unique characteristics and the formulation of consistent models. Each stage revealed something new, transforming a distant point of light into an immensely valuable case study for modern astronomy. In light of all the accumulated analyses, the explanation most widely accepted by scientists today is that 3I Atlas is an interstellar comet rich in carbon dioxide, whose early activity and apparent instability result from the sublimation of light volatiles in highly porous internal layers. This hypothesis is considered the most consistent because it simultaneously explains the observed chemical composition, the irregularity of the light curve, and the small non-gravitational deviation detected. It is not an extraordinary behavior, but rather a clear example of how comets formed in cold environments can react intensely to even slight increases in temperature. Another reason this hypothesis stands out is that it aligns well with models of comet formation in the outer regions of planetary systems. It is likely that 3I Atlas formed in a very cold protoplanetary disk, where compounds such as CO2 and CO remain stable and abundant. When it was ejected from its original system, a common process during the formation of giant planets, the object would have preserved layers rich in these volatiles. Now, upon encountering a significant source of heat again, these layers react quickly, creating asymmetric jets and bursts of activity. Hypotheses involving internal fractures also remain strong, but they are viewed as complementary rather than as the main explanation. Many comets, including those in the solar system, develop fissures along their trajectories, especially when they repeatedly pass near the Sun. 3. Atlas, in contrast, spent most of its existence in extremely cold environments, which may have preserved fragile internal structures. The sudden heating upon entering the solar domain would be enough to activate these unstable regions, producing outbursts and subtle changes in brightness. On the other hand, some theories that were initially considered promising lost strength as new data were gathered. Models suggesting the presence of exotic materials or unusual physical processes have become less likely because the observed phenomena can be explained by traditional comet physics. Even the non-gravitational deviation, which in some cases has sparked more intense debates, such as with Oumuamua, remains within the expected range for active comets. Thus, the scientific community tends to avoid interpretations that require unconventional mechanisms without necessity. The hypothesis of complete nucleus fragmentation is also considered unlikely at the moment, although there are signs of coarser dust release and brightness outbursts. No data suggest catastrophic mass loss or the splitting of the nucleus into large fragments. The recorded activity seems more associated with transient behaviors than with a continuous destructive process. This reinforces the idea that 3I Atlas is undergoing a natural reactivation phase, typical of comets that once again receive energy after existing in extremely cold environments for millions of years. Despite interpretative advances, it is important to emphasize that part of the mystery remains. Science operates with probabilities and models, and many fine details about the comet's internal structure will likely never be known with total precision. The minimum distance the object will maintain from Earth prevents extremely detailed observations, and without a space mission to intercept it, uncertainties about its deep composition will always persist. Even so, these gaps are not shortcomings. They are part of the beauty of scientific investigation, where each discovery generates new questions. Ultimately, the current consensus points to an elegant and realistic explanation. 3I Atlas is a natural messenger from deep space, whose unusual behavior reflects the diversity of environments in which comets can form. There is no need for extraordinary mechanisms, much less sensational interpretations, The object reminds us that the universe is vast and varied, and that even perfectly plausible phenomena can challenge our initial models. This final interpretation, still open to refinement, resolves the major mystery while preserving the wonder of exploring the unknown with scientific responsibility. As 3I Atlas slowly drifts away, gliding toward the outer regions of the solar system, we're reminded that every interstellar object is a time capsule traveling for millions of years. The vastness of space is not just a stage for grand phenomena, but a cosmic archive, where fragments of distant worlds silently navigate between the stars. The comet's journey echoes the idea that the universe is always in motion, always changing, carrying with it stories we can only partially decipher. Even so, every observed detail becomes an essential piece of a larger puzzle. The passage of an interstellar visitor compels us to reflect on our own place in the cosmos. We are passengers on a small planet orbiting an ordinary star, and yet we possess the extraordinary ability to detect, study, and attempt to understand objects coming from places we will never see. This duality, being tiny yet curious, is one of the most striking hallmarks of the human adventure in space. 3I Atlas, in its brief appearance, reinforces exactly that. How rare it is to encounter something like this, and how valuable it is to make the most of every collected piece of data. As we watch the comet fade into the darkness, we realize that its trajectory is more than a simple orbital calculation. It is a reminder that the universe is not static, but a sea of continuous motions. Comets like this one cross the galaxy at the mercy of gravitational perturbations, interactions with stars, and distant collisions. Nothing remains fixed for long, not even entire planetary systems. And in this constant flow, we are granted unique opportunities for science and inspiration. The reflection deepens when we consider what may have happened in its original system. Perhaps 3I Atlas was launched into deep space during the turbulent formation of giant planets, or perhaps it was deflected by a neighboring star in a close encounter. Each scenario is plausible within the physics we know, and both remind us that planetary systems can be just as dynamic as our own. By studying this object, we learn not only about it, but about the very formation and evolution of worlds. The silence with which the comet now travels contrasts with the intellectual noise its passage stirred within the scientific community. Researchers debate, compare models, adjust hypotheses, all because a small icy fragment dared to cross our cosmic neighborhood. This constant exchange of ideas shows how science evolves, not with definitive answers, but with an ongoing dialogue between observation and theory. 3I Atlas may move on, but the impact of its data will remain with us. And there is something deeply poetic in knowing that, as it vanishes into the dark, it will continue its journey for millions of years, perhaps visiting other distant planetary systems. We do not know if some extraterrestrial observer will see its faint tail crossing their sky, but the possibility, however remote, reinforces the universal nature of these cosmic travelers. They belong to the entire galaxy, not just to us or to the place where they formed. In the end, 3I Atlas leaves us with a simple and powerful lesson. The universe is far too vast to be fully understood, yet close enough to be touched by our curiosity. Every interstellar object that crosses our path, no matter how discreet, will remind us that we are part of something much greater. And it is precisely this blend of mystery and knowledge that makes scientific exploration one of humanity's most beautiful journeys. A journey that continues, as silent and as defining as the comet we have just witnessed.